So we'll start with QTA 14 machine learning methods. And just a minute, some lag. Okay. So these are learning objective, philosophical and practical differences between machine learning techniques and classical econometrics. Differences among the training, validation, and tests data set samples, how each one of them is used. Understanding the differences between and consequences of underfitting and overfitting, proposing solutions. Principal components analysis has not been discussed in detail in any of the chapters. In fact, it is there in VRM chapter, one of the VRM chapters. It is there in this chapter. It is also there in part two. In part two, still you will find a little bit of detail in FRM part two, but in FRM part one, only basic discussion of PCA is there, and one particular example has been used, which you have to just understand what is going on in that example. The derivation, the mathematics, nothing is discussed, nothing at all. Okay, how the numbers have been calculated, nothing is discussed. Then K means algorithm, NLP, natural language processing, and differentiating between these three forms. And finally, reinforcement learning. So remember, this is not a general machine learning methods chapter. This is a chapter very specific to the FRM curriculum, the way that they expect you to learn and solve questions in the exam. Okay. Some parts, of course, we'll do something, some extra parts, some extra discussions we'll do, but mostly it's about the exam. Okay. Now, so we'll start with the essence. Machine learning, which is often called ML, is is a broad set of techniques, okay, that allows computers to learn patterns from the data without being explicitly so sorry without being explicitly programmed for every single rule. So you feed the data into the models, okay, and they figure out trends or figure out relationships which are hidden in that data. Okay, so for example, you might train any model on historical stock prices and say macroeconomic indicators to learn some trends. Okay, say how interest rate will change, and those changes will impact certain sectors. Let's say we were discussing 9 sectors, right, last time. So how the interest rate changes will impact these 9 sectors. If you want to understand, it can be used. Machine learning can be used. Okay. So once these patterns are learned, they are usually applied in two ways. You have prediction and you have classification. So prediction, like forecasting tomorrow's sales or say house prices or say portfolio's expected return. It's like that. Classification is basically, you have to make a decision between say two or three groups. Like for example, if you have a loan, that loan is a high risk loan or a low risk loan, or if you have a transaction. Most common application if you see in credit in credit risk for machine learning, fraud detection. So if the transaction looks like fraud or not fraud. Okay. So basically we are kind of like, we are in the GPT days now. So we are kind of like building a smart assistant which watches the data, learns from that data, and then helps you to classify or predict new situations. Now let's understand the differences between classical econometrics versus machine learning. So classical econometrics was developed by statisticians primarily to answer questions in economics and social sciences. Okay, so the main focus is to understand relationships and do some the hypothesis testing and all those things come under classical econometrics. So basically you are building models that tell you why something happens. Okay, there is strong emphasis on interpretation as well. In machine learning, it has been created primarily by engineers, computer scientists, and and you can say it has been driven by the goal of building different kinds of system that can predict and classify well and without strict assumptions. So basically the focus is on algorithms that learn from the data and then they do their job. Okay. Now in classical econometrics, we always start with economic theory. Now, many of you who might have studied economics in grade 11 and 12, you might have seen something called as demand curve. What is the slope of the demand curve? Upward or downward? Anyone who remembers?
So, so it is,
Downward slope, Nitin, or upward slope?
it depends, sir, I think.
Downward.
Generally downward. See, when you start with the basic demand curve, very basic,
Okay.
it is a downward slope generally. Okay, yeah, and you're actually right. Sometimes it may be the case where it might be sometimes in very rare cases, depending upon the goods, it might be a different case. But in general, demand curves they actually slope downward. Similarly, there was a curve which was known as the Phillips curve. Okay, it was about inflation and unemployment. It was actually again inverse kind of relationship. So these are all models. Models are built to test these relationships, to quantify these relationships. And these classical econometrics people, they want to ensure that their models satisfy the assumptions so that they can make some statements, any causal statement. Like, for example, they can say a 1% increase in interest rates leads to a 0.5% drop in investment, something like that. That can be a causal statement towards the end. So what is the emphasis? Emphasis is on theory, explanation, interpretability, okay, and consistency with that economic theory. But in machine learning, data is king. It actually flips the mindset completely. It cares very less about starting with a theoretical model. So the goal is to let the data speak for itself, to discover complex patterns, to discover relationships without imposing very strong structure before. Okay. So this is, I mean, if you have learned advanced neural networks, then you will be able to appreciate this point a little better. But just try and understand that machine learning practitioners, they are very comfortable when they treat the model as a black box. As long as their predictions are good, they are okay. Even if the model is a black box, even if they are not able to understand completely. So why I said advanced neural networks, because I mean it's almost impossible, right? I don't think it's possible for human beings to understand how exactly neural networks are working. So it's kind of like quantum physics. The predictions are very good. Okay, it models the real world very nicely. But what exactly is quantum physics? Even the best of the physicists who developed quantum physics, even they are not able to understand it properly. Okay, and that is what I mean. Many famous quotes of Richard Feynman and other physicists are in that direction only. So machine learning is about pattern discovery. Machine learning is about predictive power. Okay, and of course it can come sometimes at the cost of interpretability. You are not very concerned about interpretability. Whereas in classical econometrics, the emphasis was on interpretation. Okay. So if suppose we talk about, I mean, just now we discussed in the previous chapter, we were discussing the Fama French model, the CAPM model. So a classical econometrics person, he or she might build a CAPM model or a Fama French three-factor model. And what is the theory behind it? Asset pricing theory. Okay. A lot of assumptions are there. And she might be testing hypotheses about risk premiums. All these things can be there. Whereas in in a similar context, a machine learning person, he or she might feed hundreds of signals. I mean, what kind of signals we can have if suppose we want to predict the stock returns of next month. Generally, what signals do you use from the market? I mean, technical signals also can be there and fundamental signals also can be there, right? Anyone who will give an example of a technical signal?
Like a
Anyone who has
chart structure.
art structure? What, I mean, anything else? A little bit more specific, please. Have you heard of moving averages? 50-day moving averages, 30-day moving averages, 100-day moving average, even 200-day moving averages are there, right? So
52
moving
Yeah.
week,
averages can be there.
52
Okay,
week high.
in the chart structure, volatility clusters can be there. Okay, and of course, fundamental signals can also be there. Sentiment scores can be there for the market. Okay, so these things can be plugged together. They can be given as input in a model, and they can see what best is predicting the next month's stock returns. So whether it aligns with the theory or not, neatly, that is a different aspect altogether. They don't care about that. If the prediction is good, no problem at all. Okay, so that's the difference between the two.
Where will the
Then in
elections and all
classical
come?
econometrics, yes, please, Nathan.
Sorry to interrupt, but
No problem.
where will suppose there is a, I mean, say some government changes also happens, like which will have an impact.
Correct.
So
Correct. That
where is
also
the,
can be a signal.
it was a technical or a fundamental?
I think it's neither a technical nor fundamental because it is a factor, I think, not even macroeconomic, because probably it can be a shock, and that also can be an input.
Okay.
Okay. If it is not expected, that it can be an input. I mean, because it is not macroeconomic also, it is not fundamental also, it is not technical also. So it will not go under any hat. But yeah, that still can be a signal. That is the beauty of machine learning. It's not necessary that you have to use fundamental or technical or macroeconomic or anything else aligned with theory. Anything can be used as a signal. Okay. So in classical econometrics, you have a well-defined data set. Okay. And it's very carefully structured. Okay. Like very clean table, cleanly defined variables, income, interest rates, inflation, unemployment. Measurement will be very consistent. Okay, assumptions will be there. Data has to meet a lot of assumptions, like assumptions that we discussed. In the last chapter in regression, we discussed assumptions regarding no multicollinearity, homoscedasticity, right? All these things. All those things should be there. But in machine learning, you can have complex and unstructured data completely. It is actually built to handle messy and unstructured data or even higher dimensional data. It can incorporate thousands of variables, thousands of images. Okay, unstructured text. In fact, if you follow the Instagram page of MidhaFin, I think last to last post was about satellite pictures, satellite images to assess credit risk. Okay, so you can go through that. So it will actually, it was a very interesting post. And we try to post these kind of innovation facts and news, sometimes news also on the channel. So if you want, you can follow that. Now, what is the focus of machine learning? The focus is very less on narrow data sets, well defined data sets. Again, it is about letting the algorithm maneuver, I'll say, or manage or manipulate through large data, noisy data to give you predictive patterns. Okay. Next, classical econometrics relies heavily on the formal set of assumptions. I've given a list of all those assumptions earlier only, and in this case, strict assumptions are not required. Focus is on prediction only. Then in classical econometrics, after building the model, the analyst probably will run a series of formal hypothesis tests. It can be Z test, joint Z test or T test or joint test. T test will be that statistical significance test. F test can be joint test. Then later on in time series chapters and other chapters, you'll in fact in regression chapter also there were some tests. Okay, Bruce Pagan, Durbin Watson in time series you can have. Then what is the purpose of all these tests? You want to validate your model structure and you want to confirm the theory driven expectations. Okay, that is the purpose. But in machine learning, you do not test a particular hypothesis. The process is different. Okay, the analyst will not start with the hypothesis. The focus is on trying different models, different algorithms. Okay, we'll see different kind of criteria also, cross validation and everything. And see, in classical econometrics, what were we asking? We were asking, for example, is the coefficient of X statistically significant at 5% level? That is what we were asking till now. But in machine learning, you simply ask, does including this variable x improve your prediction power or not? If it improves your prediction power on unseen data, well and good. Okay. Then you have in classical econometrics, once you estimate the model, you actually judge the quality of the model through statistical measures. Again, this is related to the previous point. This is quite related to the previous point. Checking if they are statistically significant, goodness of fit, and all those things. Okay. But machine learning, the emphasis is on forecast accuracy. How well your model predicts unseen data or predicts on unseen data. In classical econometrics, the models are easy to interpret. So, for example, if you see multiple regression, for example, and if you want to interpret the slope coefficient, it is quite easy, right? One unit increase in x leads to some units increase in y, keeping everything else constant. Again, it aligns quite well with the economic theory. But in machine learning, as we discussed, models are often sorry, models are often like black boxes, and practitioners are completely okay with that, as I said earlier. Okay, so simple interpretation is not possible. Now, classically, the econometrics part classically has or traditionally has leaned more towards R. I'm not saying that they don't use Python or the machine learning part counterparts don't use R. No, this is based on widespread usage. Okay, so traditional lineage has been towards R because there are a lot of built-in function in R. You have when you study R, and if you have an exposure to R, there are many packages, LM test package, sandwich package, all those things are there. PLM is there. Okay, paneling is there. But machine learning favor favors the machine learning practitioners. They favor Python a little bit more because it is well integrated with different kinds of libraries. You have scikit-learn for machine learning, you have TensorFlow, you have PyTorch, a lot of things are there. And of course, these things are not a part of the curriculum at all. I'm just discussing those who are aware. You can just relate it to it. And those who are not aware, I would recommend after the exam, as I say, once you learn practical skills, only then you will be able to encash your FRM even in a better manner. Okay. So it's not about R versus Python being better. Again, this is not about R is better or Python is better. It is simply about which tool is suiting the workflow of classical econometrics versus the workflow of machine learning. That's it. Okay. So we have some advantages of ML, which again are ingrained in the differences only. So it is effective when theory is limited. Flexible functional forms to capture complex interactions, and non-linearities can be captured. Okay, now when we are doing sample splitting and preparation, okay, you have the full data set, okay, and you have different sets which you take out from the full data set. You start with the training set. So this is the data on which model actually learns the patterns. Okay, and also it estimates the parameters or maybe fits its coefficient. Okay, so it's like a practice field for the model, trying to minimize errors on this field, on this set, by adjusting the rules internally. Then you have validation set. So after the training set has been used and after multiple models have been trained and different candidates you take out from those models, or maybe you're trying different hyperparameters like complexity, penalty terms, learning rates, all those things are there. And now you have now three or four candidates from your training set, and now you want to compare these models. So this validation set answers this question that which model or which version of the model seems to perform best on, I'll not say new data, I'll say new-ish data, because that data is still not new. It's just the data which the model has not seen during training. Okay. So it helps you to tune or select the best configuration before you make any final decision. And then you have the test set. Okay, so test set is that set which is not used at all. It is completely held back from the model building and selection process. So this is your true check, out of sample check it is called, because now the data is out of sample. They were not used either in training or validation. So it tells us how your final chosen model will likely perform on real future data. Okay, so it's like I mean, if suppose training set was the practice field, you can say, and validation was probably the mock exams. Okay, so this was like, in the LMS, you see chapter wise questions and quizzes. So training set is like that for you. Validation set is like the mock test for you. Okay, and test set is, of course, like the final exam for you. Okay, no hints at all, no peeking beforehand, final exam. Okay, so once again, I'll repeat that in this case, from training, you learn the parameters are estimated, the models learn, then validation, you answer this question, which model is the best, and from test, you check how effective was your model or how effective was your preparation of FRM when you take the final exam. Okay. Now, if you wanted to, because it's all about financial risk management, then this particular part only we'll just discuss in the context of prediction or say risk management in general. If you have say stock price data, say you start from 2018, 10, let's say, okay, and 2010 to 2020, let's say, use the data to mm, train your model. Okay, maybe your objective is to maximize the Sharpe ratio. As I said, this is like your practice field, like your lab environment, where you test your ideas, you tune your ideas. Then you use the data from say 2020 to 2023, which was not used in the building the strategy, and you compare different variations that you got from the first part. From the training set, you will get say 3 or 4 variations. You check all of them in the data for 2020 to 2023. Okay, and you see what is best, which model is the best, just like your mock test, as I said before the FRM exam. But still, it's historical because that question has still not been asked in the exam, right? Now you check the data from 2023 to 2025, which has never touched you till now. Maybe some questions might be repeated in the FRM exam. That's a different matter. That is something which you can thank your luck for that day. But still now, mostly the assumption will be that maybe you have not seen these questions till now. Okay, so you will see that how will your preparation and how will your scores in the mock test reflect on your final test set or final exam day. Okay, so in terms of stocks, you can say that if you check the data from 2023 to 2025, even that is historical. See, till now, mock and you'll say, sir, and why are you relating it with the actual exams analogy? That is not historical. But let's come to that why. That is still your final test. That okay, fine. This is telling you that okay, yeah, this is the best one, and it is quite effective. You have done very well in the exam. Your preparation was quite effective. The application actually comes in the industry, in your work. Okay, based on your FRM knowledge, whether you are able to decipher patterns or not in your work, that is your real test after the exam. Okay, and that will be something which we have never seen. New scenarios will be there. So just like predicting stock returns once from 2023 to 2025, if you test your model on the data that you have never touched, okay, you will see how well your final strategy would have done on genuinely unseen data. Okay, so this is your final confidence check before applying real amount of or before deploying real money, I should say. Okay, now see the splitting of the data into these three sets this way is actually quite important because it is helping you to build a model. In fact, I should say it is preventing you from building a model which just memorizes the past. That's it. Okay, it stands a good chance to work well on new unseen data, which is your ultimate goal. Okay, so what do you do? Train on the train on the training set, tune and select using the validation set, and verify true performance using the test set. Okay, now why uh, does the type of data matter? When we talk about cross-sectional data and time series data, why do these matter? See, cross-sectional data is data which has no natural ordering in time. Okay, you can have different examples, say house prices across different cities at a single point in time. We are comparing, say, Bangalore, Mumbai, Delhi, Ranchi, Kolkata, Madras, Chennai, sorry, Hyderabad. So house prices at different across different city at a single point in time. Today, average house price. Maybe credit scores of customers, maybe income levels of customers. All these are cross-sectional data. Okay. So in this case, for sample splitting and preparation, you can use random draws because the observations are not linked by any sequence. You can safely use random draws to split the data into training, validation, and test sets. Okay, because random sampling is not breaking any kind of time dependencies because there are no time dependencies at all. But if you talk about time series data, time series we'll study in the next to next class or next class, QTA 1011. Think next class only, QTA 1011. This is where order matters. Like for example, you're talking about daily stock prices, daily stock prices. So obviously it is in an order according to date. Quarterly GDP, okay, monthly interest rate, something like that. Sales over months. So in this case, you cannot shuffle your data randomly because you would actually destroy the patterns you want to learn in that case. There can be many patterns like trends, seasonality, you would be destroying those patterns. So the rule of thumb is that you train on the earliest data, training data first. Validate after that, validation on a later period, and you test on the most recent period. You test on the most recent period. Makes sense, right? It makes a lot of sense. You should test on the most recent data. Now let us come to
So,
cross validation.
sorry,
Yes.
one. Can you just go back to the previous slide?
Yes.
So when we do the validation testing, right?
Mhm.
In that sense, we have a window to kind of, if we are not getting the right result,
Mhm.
then maybe we can go back to the previous stage, right? The training data, again selecting the data.
Absolutely, yes, yes. At any point in time during validation, if you feel that none of the variations are good enough, then definitely you can repeat the process. Maybe you can split the data in a different manner. Maybe the splitting was not perfect. Maybe you can increase the amount of training data, reduce the amount of validation data. Anything can be done. Absolutely correct. Okay. So, what is cross validation? Specifically, we'll talk about k-fold cross validation. Okay. Now, basically, it's related to the splitting of data. So the idea is quite simple over here that instead of using just one training and one validation set, we actually rotate through multiple splits to get a better estimate of the performance of the model. So this is the visualization over here. Okay, so I'll just come to the visualization once again. First, I just give an example with numbers. Suppose n is 80, that is you have 80 data points in total for both training as well as validation. Now this, mind it, this is a small number and that is where cross validation is even more important for cases where sample size is small. Now you decide to use 5 folds, k is equal to 5. Okay, so divide the 80 data points into 5 equal folds. So 5 equal folds means Each of them is having 16 data points. Okay. Now you perform 5 iterations. So in each iteration, you use for one fold 16 point for validation. You can see the remaining 4 for training. Okay. The remaining 4 for training and each fold for the one fold for validation. Okay. So this is the idea. So again, visually, we can again understand this, that in the first iteration, the first block is used for validation, others for training. In the second iteration, the second becomes the validation set and the remaining for training. And this continues until each fold gets a turn for being the validation set. Why do we do this? Again, the first reason is less number of data points. And another important reason is that this technique ensures that every data point gets to be used for validation exactly once. Okay, so you'll get a better estimate of model's performance, and it will reduce the risk that your results happened or were good because of a lucky single split or maybe an unlucky single split. So this will average it out. Okay, now there is an extreme case over here, which is known as LOOCV, leave one out cross validation. In this case, K is equal to N actually. So if you have 80 data points, you have 80 folds. How does it work? You split the data into 80 folds, okay, with each with just one data point, and for each iteration, you use 1 point for validation, 79 for training. So every single point gets its turn to become the validation set exactly once. Okay. Now again, and of course you repeat this
So
two,
this
three times.
table on
Yes.
the right hand side is not for this one, right?
No, no, no. Actually, this is the same figure from the previous one. By mistake, this figure has been included over here. Okay. So this is not for this one. Okay. Wrong. This is the wrong figure for this one. Basically, it's the same continuation. The idea is the same. So in a single validation fold, basically, in fact, you can say that this is for 5 data points only, right? So one each. Okay, so it would have been better because we cannot divide. Probably it would be very lengthy. So we'll try to adjust a figure where we'll have the dots to represent the blocks which we can't represent because of lack of space. Okay,
Yeah.
so we'll do that. We'll modify this. Okay, to be modified. So each point is getting individually tested, and the final performance is going to be averaged over all the 80 runs. Okay, so that's the idea about LOOCV. Now let's come to underfitting and overfitting. Very, very important slide. And I think, again, in the last 3 years since the machine learning chapters were introduced, a favorite topic from this particular chapter or GARP. Okay, what is overfitting? When the model becomes too complex, too large, excessively parameterized. Okay, so it is not just capturing the real pattern, it is also capturing the random noise in the training data. And of course, underfitting, when the model is too simple, it fails to capture important patterns that truly are there. Okay, so we can take an example. Let's suppose we are trying to predict house prices based on the size of the house. Okay, so what is the issue with these three? See, if you have the problem of underfitting, you'll try to fit a straight line, a linear model, maybe a very simple model, even though the relationship is curved. For overfitting, you might fit something like a 20-25 degree polynomial. So this model will bend and twist to pass through every single data point, even the random fluctuations. Okay, so model follows every point, even noise, which is giving poor generalization because see, it will look very good on your training data, but it will fail miserably on the new data because it has not generalized, it has actually memorized noise as well. Okay, So you can, and of course, good fit, you can use a reasonable curve like a 2 or 3 degree polynomial. It is flexible. This model is flexible and captures the trend well without chasing every small bump. So in underfitting, the model is too rigid, too simple, ignores the patterns. In overfitting, the model is too flexible, sees patterns even in random noise. And for good fit, it is like a good trade-off, right complexity, just the right complexity, capturing real trends but trying to ignore the noise. So this is a very good example that we can discuss. So this is a plot which shows that form a clear U-shaped kind of pattern, like almost like a parabola, right? But you have tried to fit a straight line over here, the simplest possible model. So this is a classic example of underfitting. The linear model is too simple to capture the actual relationship. Okay. So on the far left, the data points are very high above the line. Okay, model underestimates these values. You can clearly see. In the middle, data points are below the line. Model overestimates these values. On the far right, you again underestimating large values. Okay, so again, if we take an example of housing prices, okay, and we want to predict the housing prices based on the size of the houses. So very small houses and very large houses are selling for more per square foot due to some special reasons. It is possible that, see, in Bangalore also, I mean, in the last 2 3 months, the kind of research, whatever small little research I have done, and I was a bit surprised also that the prices, I mean, if we have 1 BHK, 2 BHK, 3 BHK, of course, there is some uniformity with respect to the per square foot price. But surprisingly, new projects, particularly in North Bangalore, I'm seeing that the prices of 1 BHK are a little higher in terms of per square foot price, and also 3 BHK in only new projects I'm telling, especially closer to the airport, some premium projects. But the prices of 2 BHK are a bit depressed. So that can happen because of special market dynamics. Maybe people want to buy 1 BHK more because of only investment purpose, and there are too many clients for that. Okay, and for 3 BHK also because of the extra bedroom, or maybe the supply is less. That is also possible. Maybe a lot of 2 BHK projects are, anything can happen. So market dynamics, supply issues, and because of that you have a U-shaped pattern. But if we are using a simple model, what we are doing, we are actually underestimating the prices of these extremes, whereas overestimating the price of these means. The mid-size houses, we are overestimating the prices, because what we are doing, we are trying to average everything out. Okay, so quite rigid model, quite simple model, completely failing to capture the curvature in the data. Now let's see the next case. Now this plot shows the same data points as before, the same points, but this time we have fitted 20th degree polynomial. Okay, extremely flexible, classic case of overfitting. It is so flexible that it twists and turns dramatically just to pass through nearly every single data point. Okay, so it is not only capturing the trend, but it is capturing, in fact, the noise even more present in this data set. So it looks very good, it is fitting the current data set perfectly, but it will perform very poorly on new data because it has memorized noise also rather than only the general pattern. Okay. So this is a problem where we say it has low bias but high variance, and we'll see this later on. Okay, so again, we can use the same analogy of housing prices. Suppose we are trying to predict the prices based on size. Now, instead of having a very smooth relationship, we create this hyper complex polynomial or hyper complex rule, which says that, let's say if you have a 1500 square feet house, okay, the price of the 1500 square feet house is say 1 CR, okay, 1 crore Indian rupees. Okay, and just for the international candidates, we are talking about 10 million Indian rupees. Okay, so 10 million Indian rupees. But let's say a 1550 square feet house is say 1.5 cr or 15 million rupees, and then suddenly a 15-25 square feet house, it is going to 90 lakhs or 9 million only. So it is a very complex relationship. Every single noise you have captured, you have not considered the individual characteristics of the house. Maybe that is a corner plot. Maybe the winds are better. Maybe the view is better. A lot of things. Of course, the companies factor all these things into the cost, and for every single property they add all these costs, the floor rising and everything. But I'm saying, let's say in general, other factors can also be there, right? So the rule is overfitting the noise also of your data, and if it will not generalize good to future predictions. Okay, now this is a quadratic function, a simple curve which we call as a parabola. Compared to the earlier linear fit, this model is much flexible enough, I should say, to capture the main pattern, curved pattern, but it is not as wild or as wildly flexible as the 20th degree polynomial that we saw earlier in the previous slide. So this is an example of a just the right model. Low bias, okay, because it can model the actual curved relationship, and a controlled variance. It does not twist and turn to chase every tiny fluctuation. Okay. So obviously in the housing prices example, you can clearly see that quadratic relationship will capture that small houses and large luxury houses, they both can have higher prices per square feet. Okay, and mid-size homes like 2 BHK are more standard in general. So smooth curve without reacting to every little odd sale, it hits the sweet spot, you can say. So let's break down again and let's see the differences for overfitting and underfitting. So the model becomes too complex, excessive parameters in overfitting, and it uses too many features or overly flexible functions, you can say. Too much random noise, not just the pattern. Low bias, but high variance. So it fits the training data really well. If a model fits the training data really well, it will have low bias. But if it fails on new data, it will have a very high variance. Okay. And it is a bigger problem in machine learning because machine learning often tries to have very flexible models. So overfitting is more of a practical concern in machine learning. Underfitting, too simple, doesn't capture key relationships, key parameters missing. Monotonic connection, it assumes a simple linear or a single direction effect, misses out on complex patterns, you can say. It is biased but stable, low variance. Predictions are very off, very high bias, but they don't change with change much with very new samples. Okay, so low variance. And of course, this is a bigger issue in classical econometrics. Okay, the classical econometrics focuses on simple models, interpretable models. So obviously, underfitting due to omitted variables will be a main worry, which we saw in multiple regression also last time. So this is one of the most important graphs that not only you will see in this chapter, in fact, all across wherever a machine learning course is there, I think this graph is present everywhere. This is the bias variance trade-off graph. So how do you balance making your model complex enough to capture the patterns, but not so complex that it memorizes all the noise as well? So on the x-axis, you have model complexity. On the y-axis, you have error. So what is the trade-off? You have this curve bias square and you have this curve variance. Bias curve square, it shows how error due to extremely simple model, extremely simple assumption, they actually drop as the model becomes more and more flexible. Okay, you can clearly see that for low complex models, the bias square is quite high. Okay, Simpler models are very rigid, very high bias. Variance curve does the opposite. As the model becomes more complex, it starts reacting to you know, too much reaction to random noise. And the prediction will change widely with different samples, which will increase the variance. And the total error in this curve is the sum of variance plus bias square. So total error is equal to bias square plus variance. Okay, how do you find the sweet spot as I said? So this you can see over here is the optimal model. It's a good trade-off because to the left of it, you can see that there will be underfitting. Underfitting will start actually to the right of it, you have overfitting. Okay, now before you feed the data into machine learning models, you need to scale it or you need to transform it so that the features are on similar ranges. Okay, actually, this is important because many algorithms become faster. They start to perform better if you standardize or normalize the data. So, how do you do standardization? Same standardization that we have done earlier from starting from chapter 2. X minus mu divided by sigma. Okay, so this helps put the features on the same scale, completely same scale. And do you remember uh, what was the mean and sorry, actually, it's already given. So if suppose you have different sources, different units, then standardization will remove the units and all. The normalization creates a variable that is bound to be between 0 and 1. This is the formula x minus x min by x max minus x min. So if you want to fit all the values within a small bounded interval of 0 to 1, this is the best way out. You can think of it like stretching or squeezing the data so that the smallest value becomes 0 and the largest value becomes 1. Now, which one is preferred in which case? Okay, so when data set contains outliers, then standardization is preferred over normalization. Okay, because see, normalization depends heavily on the min value and the max value. It's quite clear, it's quite obvious. So if you take the min and max value and you normalize it, it will distort the entire scale, right? Because the min or max may be too high because they're outliers. So that's why we'll go for standardization. Standardization is simply spreading the data around the mean, so it's much more robust. Then you have data cleaning. Data cleaning is helps in eliminating these issues: inconsistent recording, unwanted observations, duplicate observations, and outliers and missing data. Now let's come to the important part. You have types of machine learning: unsupervised, supervised, and reinforced. Reinforcement learning or reinforced learning. Okay, now what is unsupervised learning? Unsupervised learning is a type of machine learning where the model tries to find patterns in data, okay, via clustering and without any label. So it uses unlabeled data. There is no target variable telling it what to predict. Okay, we'll see that this is very different from supervised learning, where we have clear cut input output pairs. Okay, so maybe data clustering can be one of the methods. Okay, so as I said that since it works on unlabeled data, there is no defined goal like you have to predict a category or you have to predict a number. Maybe sometimes it is just a useful way of reducing complex data into simpler data, more meaningful components. It will capture the minimum amount of features, but probably the most relevant features. Okay, so minimum yet relevant features, and some of the methods are principal component analysis and k-means algorithm. Principal components analysis, as I said, very limited discussion is there. It helps us in reducing the dimensionality of the data while keeping most of the important information. And k-means clustering groups similar data points together into clusters. Okay, so let's say you are uh, feeding in thousands of you know news headlines or reports without any topic labels. No topic labels. Okay. Now the model will try to find out hidden structures or hidden topics or hidden themes. Okay. For example, it might automatically group the articles into different topics like interest rates, oil prices, earnings season, all these things. So this is quite useful for those kind of analysts who just want to understand very quickly what themes are trending in financial markets without even manually reading or tagging thousands of articles. Not required. Okay. So again, unsupervised learning is about letting the data speak for itself, uncovering the patterns in that data, which we might not have noticed till now, and organizing different kinds of information, complex information, into meaningful information. Then we have supervised learning. Supervised learning is a type of machine learning where we train the model using labeled data. So inputs are paired with known outputs so that the algorithm will learn to predict the output from the input. Okay, you want to classify data into categories, classify the observations. Okay, or you want to predict the value, maybe regression. That is also one type of supervised learning. Okay, a simple one, although very simple. What is labeled data? Okay, labeled data is that data which has been tagged or labeled or classified together with the correct output. So if you have a data set of, let's say, different transactions from the past, okay, then you can label every single transaction as fraudulent or non-fraudulent, fraud or not fraud. This is how the model will know how to learn. Okay, so again, we can take that example of fraud detection. So you train the data on the past transactions labeled as fraud or not fraud. Okay. And then once the model is trained, you look at new transactions and you decide if they look suspicious or not. You'll compare it with patterns that the model learned from the past data. Okay, that is exactly how many credit card fraud detection systems work in practice. Okay, so basically, supervised learning is about learning from examples where answers are known so that you can make predictions or classifications on new or unseen data. Okay, now reinforcement learning simply uses trial and error strategy to make sequential decisions in dynamic environments. Now, let's briefly introduce principal components analysis. It's a well-known statistical technique for dimensionality reduction. So in simple terms, it actually helps you to take a complex data set with lots of variables and boil it down to a very few core variables, core factors, which capture most of the original information. Okay. So if suppose you have, say, we were talking about signals, indicators, like let's say you have different indicators. Okay. You have 20 different indicators. You have price to earnings ratio, you have dividend yield, volatility and everything. Many of these are correlated with each other. So what principal component analysis will do, it will combine them into a smaller set of new variables, which will be known as the principal components. So instead of 20, maybe you're left with only 4. They will capture the most important patterns. Okay. And these new components, okay, they provide the same information as the large number of correlated variables, and these new components will be uncorrelated with each other. Okay, so in machine learning, it helps to clarify the underlying origins of any kind of ambiguity or clarify the underlying sources of variation. Okay, now one example which we are going to see is yield curve example. In finance and risk management, this technique is used to simplify yield curves. So instead of tracking yields on different maturity, dozens of maturities, we might just find that three principal components are explaining almost all of the movement for the overall level of rates. And that is exactly what is done in this example, which I told is there in this book, QTA 14, this chapter. It is there in VRM book, and it is also there in FRM part 2. Okay, so let's look at that example. So classic example from finance, the relationship between interest rates and the maturity of debt. Okay, so how many uh, factors are there? If you see, you have 1 month, 3 month, 6 month, 1 year, 5 year, 10 year, 20 years. So you have 1, 2, 3, 4, 5, 6, 7. 7 factors are used to explain all the rates, but these 7 are also highly correlated. So rather than using these 7 factors in your model, what you can do, you can just use the principal components of. So PCA will reduce this complex set of correlated yield changes into a few uncorrelated explanatory factors. And again, as I told you earlier, how it has been derived, why these components have been found out, and how not at all a part of your course. What are those components? Only that you need to remember and understand. So the first principal component, it, it is actually the parallel shift in the yield curve. And don't worry, if you don't understand it right now, this is just getting introduced. Shifts, twist in yield curve, we'll discuss a lot in great detail later on. So don't get nervous at all. Even if you are able to understand nothing from this slide, completely okay. You'll be able to appreciate it better when you understand yield curves properly. Okay. So this first principal component, it represents a parallel shift in the yield curve. So it means that all interest rates will either move up or down together by the same amount. Second principal component, it captures a twist. Twist means short-term rates are going in one direction, long-term rates are moving in another direction. So if the Federal Reserve, for example, or the RBI, it increases the short-term rates, okay, and if the long-term expectations are not changed, then obviously it will be a twist. Third component is a bend or curvature. So it means that short-term and long-term move together, mid-term moves in the opposite direction. Okay. So this is a table of PCA loadings from a real world analysis. Okay, each column is showing how strongly that maturity is loading into the principal component. Again, the mathematics is not important at all. The important point that you need to understand from this particular image, this particular table, is that, and it is quite impressive by the way, the first 3 components explain more than 99% of the variation in the yield curve. Okay, so despite having seen 7 separate yields, 1 month, 3 months, 6 months, they are not required actually. You can describe almost everything happening with just 3 uncorrelated factors. So this not only simplifies your risk management and hedging, but it also tells you that most movements in yields are driven by only a few systematic factors. That's it. The K means clustering algorithm. So what is this K means algorithm? It is actually one of the most popular unsupervised learning algorithms, which is used for clustering data. Okay. So there are no labels since it is unsupervised. No labels are there. Okay. You don't know which group each data point belongs to. It has to be clustered directly from the data. So K means is trying to discover natural groupings in the data. And how does it work? It follows this 4 step process, which again is iterative. So it's an iterative process. It has to be repeated. So you start by uh, selecting randomly initial values for the K centroids. And why we are calling them centroids, we'll come to that. So basically, they are in the cluster centers are known as centroid, and you pick K initial cluster centers randomly. Okay. So just think of it like, you've chosen, okay, this is my value for K, and you have dropped K pins randomly on your data map. You have a data map, and randomly you drop k pins on those data maps. That's it. Next, you assign each data point to the nearest centroid. Okay, so just imagine that every point is asking which pin am I closest to. Okay, it then joins that cluster. Okay, then what you do, you update or recompute all the centroids. You are finding, see, why you recompute the centroids? Because randomly first you have assigned the centroids, then each point has asked itself that, okay, which pin or which center am I closest to? It has been assigned to that cluster. But once on clusters have been formed, then you recompute all the centroids. Why? Because now you want exactly the center of that cluster to be your new centroids. Okay. Then you repeat steps 2 and 3 until the centroids no longer change. Because see, once the centroids will change, the points will switch the clusters. Okay, so this has to continue until the centroids will stop moving much. It means that the clusters have now stabilized. So no longer change. I think they should have added to a reasonable degree over here, because getting the change to be exactly zero is going to be unnecessarily hectic. Once you have got a decent enough approximation of the clusters, it is good enough to go. Okay, so in risk management, especially from a bank's point of view, what can be the application of this k-means clustering? Suppose I am a bank manager and I want to group my customers based on their spending patterns. Okay, just spending patterns. So obviously what I'll do, I'll just start by placing, say if I want to have 10 groups at random. I mean, I've chosen this value of k at random. So I start by placing 10 hypothetical customers profile at random. That is my k. K is equal to 10 in my case. And then I see which customers are most similar to which profile. So 10 random customers are there. Okay, 10 random customer profiles. And then I compare the other customers with these 10 random customers. And I see, okay, this customer is closest to maybe the second profile. So what I'll do, I'll club that customer with that profile. Then what I do to update my centroids, this third point, what I do, I actually update each profile to be the average of all the customers grouped to it. Okay, this becomes my new center, new profiles now. Okay, so I'll keep repeating this process, and of course I will have different groups like, say, high spenders, say low spenders, high savers, young savers, small business owners, anything like that. Okay, so this is actually a very fast, a very simple uh, K algorithm for large data sets, and it helps you to uncover a lot of hidden patterns. Now, when we talk about distance, see, when we pick our center clusters, the second step was assign each data point to the nearest centroid. How do you measure that nearest? How do you measure that nearest?
The
Okay,
measuring
so
the
obviously you need
distance.
to have some
Yeah.
measure of distance. Yes. What kind of measures we have? Two measures we have actually. We have the Euclidean distance and you have the Manhattan distance. Okay. So Euclidean distance is as the crow fly. It is also called as the crow fly distance because it's the straight line distance. So basically you draw a straight line from one point to the other. That's the distance. Okay. And then Manhattan distance is just like, the name itself Manhattan, because Manhattan has been divided into different blocks. Okay, so like different grids, you are moving through blocks and grids. You cannot cut diagonally through buildings. You have to move block by block. Okay, so something like this. This is the Euclidean direct distance and this is the Manhattan distance for this road and this road. Okay, so the calculation is quite straightforward, very easy. So this comes from the Euclidean distance formula, comes from the same. Pythagoras theorem, the same distance formula that we have done in our school days, exactly the same. Okay, and of course for Manhattan distance, you just have to add the absolute value of these two. That's it. Then what you do, you now measure how well your k-means clustering has performed, and this is where you use the idea of inertia. What is inertia? See, uh, again, we can take that same example where we dropped the k pins randomly and we clubbed the pins together with the nearest point. Okay. So for each data point, what we did, we calculated the distance. Okay. How far it is from the center it belongs to. Okay. What we do now, after the recomputation of the centroids, once the clusters have been, finalized, what we do, we calculate again how far, we can use the Euclidean distance, no problem at all. How far each data point is away from its centroid, then we square its distance, and then we add all these square distances for all the data points. So inertia is basically the sum of square distances of each point from its assigned cluster center. Now, why do we care about inertia? We care about inertia because the lower the inertia, the tighter our cluster are and the better that cluster fits the data. Okay. And how do we use this to decide on the best clustering now? For any given value of k, the best clustering is the one for which the inertia is the lowest. Okay. So what we can do, we can first understand the idea that as the number of centroids increases, the inertia will never rise. And it makes sense also because if you compare it with the extreme case, see, every single time you increase the number of centroids, it will never rise. Either it will stay constant or it will go down. You can relate it to the analogy of R square. Remember R square from linear regression? What happened to R square? R square always either increased or stayed constant, right? As the number of variables increased. And opposite was the case with RSS. RSS never rose. It never rose as the number of variables increased. Either it stays constant or it reduced RSS. And that is why R square always increased. Okay. So it's something like that. Because see, once you add more and more points, more and more centroids, obviously each point is likely to be closer to its nearest centroid. So the total distance will decrease. There is no doubt about that. Okay, and that is why, in fact, when k, as I told you, you can appreciate it better when you understand the extreme case. So when k is equal to n, it means the number of data points is equal to the number of centroids. So each point becomes its own cluster. And since there is no distance between a point and its own center, which is itself, the inertia drops to zero. Okay, so the idea is if you keep on increasing k, you will keep lowering the inertia. But again, the problem is too many clusters means that you're overfitting. This is again analogous to overfitting. You don't need too many clusters. You will lose general patterns. You will become too specific. Okay, so what are the popular ways to choose k? One is the screen plot or the elbow plot, and the other is the silhouette coefficient. So in screen plot, we plot the inertia for different values of k. And the point where the drop in the inertia starts to level off a little, it means the drop is not too high now. It will be similar to an elbow line in the graph, and we'll see that in the next to next slide. That is the best choice. And silhouette coefficient is a bit mathematical. It measures how well each point fits within its cluster. So any higher, just remember for this rule, a higher silhouette coefficient or higher silhouette score means better defined clusters. So the objective is to choose that K where inertia is low, but adding more clusters or adding more values of K, increasing the value of K, doesn't improve it much. So try and avoid underfitting as well as overfitting. So again, We need to find that sweet spot. So let's take an example for k-means clustering. So we are looking at some data points where the x-axis shows stock returns, basically the stock, how much they are going up or down, and the y-axis shows the treasury bill yields, which are short-term interest rates. Now, each little dot represents the point in our data set. It may be different observations over time or different stocks on different days. I mean, we're not concerned about that. The plot is something which we are more concerned on. Now, what we have done is we have run the k-means clustering algorithm and we have chosen the value of k as 2 at random. Okay. And we have divided it into two clusters. Okay. So the algorithm tries to minimize the distance between the points in each cluster and its center, which we call the centroid. So these centroids, you can see they are marked in yellow. Okay, so the algorithm started by picking a random point, just like the four step, and then it iteratively adjusted the centroids. It assigned each point to the nearest centroid, and then it moved the centroid to the mean position of all the assigned points. And process, of course, is repeating until the centroids stop moving. So we get these two clear clusters, one on the left with generally lower returns, and one on the right with generally higher returns. Although both of them are having a variety of T-bill. I mean, over here you can see T-bills are lower and higher. In this side also you have lower and higher. So only about it has basically bifurcated. Probably more focus has been on stock returns. Okay. So we have probably tried and identified two different market regimes or market behaviors. Maybe this is a period of market stress and this is a bullish period or a normal period for that matter. Okay. So the important question is, was choosing two clusters the correct call? Because I told you randomly we chose two clusters. Was it the right call? Why not three clusters? Why not four clusters? Why not 10 clusters? Okay, that's where that elbow method comes in. Okay, so this chart shows the total within cluster sum of squares. Okay, basically inertia only, nothing else. This is inertia. Okay, and this is K. So as K increases, obviously the inertia goes down. But at some point, I mean, as you move ahead, you see that the improvement is not substantial as you're increasing the value of K. The improvement is not substantial. There is improvement, but not too much. Okay, so again, a classic trade-off, just like we discussed, overfitting and underfitting. So too few clusters, you are simply oversimplifying and you are missing the real patterns. Too many clusters, you are just fitting to noise. So you settle on the optimal K, which probably seems to be around this part. This is the elbow. Now, can you see if you put your right hand on the table and lift it up a little bit, probably this is your elbow. So this elbow shape, this elbow where you are getting is the optimal value of K. Okay. So is the idea clear? K means clustering. Visualization is clear. The idea is clear. The sad part is again, no programming or numericals are asked in this. So, I mean, maybe the inertia calculation will be asked maximum, but the theory is more important. The concepts are more important. Okay. There's nothing to solve over here. Is it clear? Abhirami, Alok, Arijit,
Yes.
come on. Yeah. Okay. Ujjwal and has replied. Yes. Okay. Bukola, it's clear to you. Arijit, Abhiyank, Gaurav, Mukesh, come on. I understand it's a very theoretical kind of quant chapter, although it's in quant.
Gotcha.
A lot of theory is there, but still we need to interact. Okay, Raj Lakshmi, what about you? Siva, right? Okay, fine. So this is all about K-means clustering. What are the disadvantages? Number of clusters must be specified beforehand randomly. It produces spherical clusters. Then let's come to natural language processing. We'll shift gears a little bit and we'll talk about another fascinating area of data science, which we are seeing extensively nowadays, NLP or natural language processing. Sometimes it is also called as text mining. Okay. It aims to analyze and understand human language, whether spoken or written. Okay. So it is all about getting computers to analyze and understand human language. So we are in a very different era now where we are seeing NLP being implemented extensively nowadays. Okay. Now, what are the uses of NLP? These are the major uses in finance and risk management. Okay, and other uses also. Some of the uses, of course. If you analyze text in financial statements, okay, like audit reports or even emails, NLP can pick up on unusual language patterns that probably may signal manipulation or some kind of fraud. So it is like a linguistic early warning system. Okay. Then you have purpose identifications. So if suppose you have thousands of loan applications, or say you are a startup founder, you have different investment proposals, and you want to quickly understand the or let's say you are an investor only, and you get different investment proposals from different founders, that will be more suitable, I think, over here. Okay, and you want to quickly understand the purpose. Are they uh, are they seeking funding for expansion, or say repayment of debt, or going into some risky venture? So NLP can automatically recognize this. Then you have text categorization. This is classic NLP. Automatically tagging or organizing documents into topics, right? So without manual readings, thousands of research articles can be categorized, sorted into themes. That is it. Then sentiment identification is very big in finance and other aspects as well. I mean, in marketing also, sentiment identification becomes very, very important. So this is where we train the models to detect emotions or opinions in text. Okay. So when you have a earnings call transcript, let's say you have a earnings call, is this a upbeat call, or is it a negative call, or is it a call to be cautious? Okay. Or when you go to X, are the tweets on X about a particular company very positive tweets, negative tweets, neutral tweets? So sentiment analysis is important because it gives you an idea of the market sentiment. It turns raw human language into data which you can analyze and understand. Okay, and it's so NLP is like a way of giving machines an exposure, you can say, or a window into how humans communicate. Advantages: faster and more accurate results, eliminates biases. Okay, so what are the steps? The first is you capture the language in written or spoken form, then you pre-process the text. Pre-processing is very, very important. Very, very important. Analyze it for a specific objective. Okay. Now, as I told you, pre-processing is extremely important. Okay. So in pre-processing, you tokenize the passage. So you break the text into individual words or sentences, and then you remove stop words. So this is the first step. Then you remove stop words. So eliminate non-informative words like the, is, and. Then you have stemming. So you reduce the words to their root form by chopping suffixes like running changes to run. Okay. And then you have lemmatization, convert word to their dictionary base from using the context. So maybe better, nice, all these things together can be converted to good. Okay, even over here, multiple past tense. So ran can also be converted to run. Running can also be converted to run. So present tense, past tense can be converted to the same root verb, root form. Over here, different words having the same meaning can be converted to a base meanings, forming some context. And then you have n-grams analysis. You extract sequences of n consecutive words. Okay, so for example, bigrams like machine learning together. Machine separately, learning separately, in isolation won't work. Machine learning together. Bigram. You can also have trigram. Multiple grams you can have. Okay, so that is the idea. Now comes to the we come to the last part of this chapter, reinforcement learning, and finally we'll see the differences between the three classes. So the goal of reinforcement learning is to create a policy for a sequence of decisions in order to maximize a reward. The requirement of a large amount of training data is the biggest drawback. So a massive amount of training data is required in reinforcement learning. And a machine built in this manner will make many errors and perform badly at first, but it should improve significantly with experience. Working of reinforcement learning is based on states, actions, and rewards. Okay. So states define the environment, actions are the decisions taken, and rewards are the results of those actions. The aim is to choose the decision that maximizes the value of total subsequent rewards that are earned, and a discount rate may be used to determine the value of total subsequent rewards. Now, this is the idea, an estimate of the value. See, once we deal with this example, we'll be able to appreciate this slide, this part of the slide, in fact, much better. So the idea is that on repeated trials, the algorithm learns an estimate of the expected value of taking action A in state S. This is usually denoted by Q and it is referred to as Q value. Now remember, this part I think should have been emphasized in the GARP example, which probably they have missed, because where they have said it correctly over here, that an estimate of the value being in state S at time t is given by Vs is equal to max QSA, which means the current best action is to take in state S is the value of A that maximizes this expression. Okay, but the example, the numerical part which is given, this part should have been reiterated to appreciate this part. Okay, but you need to understand these two things very, very, very carefully. That there, of course, there will be two strategies. One will be exploration. Exploration will be when you are in trying to the agent is trying to go for a new action, and it is assigned as a probability of 1 minus p. Exploitation, the best action which is already known to the agent, and it is assigned a probability of p, which makes sense, right? There can be only two options. Now, in the early days, when even AI ML was not completely formalized like it is now, the early days used to have, in fact, I think chess algorithms or chess computers, supercomputers have been into operation since decades now, correct? If I'm not wrong. So we have seen that they have consistently outperformed humans since a long time, right? I mean, now almost it has become almost earlier. So still there were instances where computers were beaten. Now I don't think it's possible because if I remember, I think for Magnus Carlsen, the uh, I think the what do we call it? The score? I forgot. What is the score called in chess? Uh, what is the score called? Can you just tell me? Rating or what? Chess rating, correct? Or score, something like that. In classical blitz, all these things are FIDA. No, FIDA is actually no usual. Actually, there were uh, two parallel organizations which were running. That's FIDA is, and in fact, I think in 1996 or 1997 this split, and then FIDA became separate, and then after 20 or some odd years they again merged. So I'm not talking about the organization. Is it known as the rating only, chess rating, or something? Any special name is there? I think it's the rating only, right? What is your rating? That is what they asked, right? Correct. So, what was the maximum, the peak rating of Carlson? I think it was close to 20, just less than 2900, correct? 28, in the higher 2800s, correct? Higher side of 2800s, correct? But I think the supercomputer that we have currently probably has a rating of more than 3600, correct? Can you check? I'll just check it once again. Wait. Chess highest rating. Let me just check. Yeah, well over 3,000. ELO. That is what I was saying. ELO rating. So 3600, correct. So Stockfish, one of the top engines, is estimated to have an ELO rating of 3644. Okay. So now it is not possible, right, for humans to beat the supercomputers so easily. And in fact, probably impossible now. So this idea of exploration and exploitation has been into picture since those early days, when it was just being, although they were not 100%, even they did not knew that they were actually the pioneers of machine learning only. These techniques which were being used was the technique of reinforcement learning only, but that strategy was exploration and exploitation only. Correct. So if the computer has identified that, okay, this is the best move in this scenario, it will go for exploitation. Or else, if the computer is still learning, it may go for sometimes exploration, sometimes exploitation. Okay. So to find out the best strategy, two methods are used. You have Monte Carlo method. In Monte Carlo method, the total subsequent rewards are important. Okay, the total future reward, which is called as total return, but that is only known at the end of any episode. So you have to wait until the entire thing finishes or until the game finishes or the episode finishes, and then you add all the rewards you got from the point you took the action till the end. Okay. So Monte Carlo updates everything after the whole episode's end. That is why the formula is this, where R is the total return, total subsequent return. Okay. Alpha is 0.05. It is chosen after some experimentation. I'll just give you a brief on alpha also. Again, this part I again feel that it has not been emphasized properly in the book. They should have emphasized it properly. Then you have temporal difference learning. Okay, it only looks one decision ahead and it assumes that the best strategy identified so far is made from that point onwards. Okay, so this learning updates Q values after every steps, not just full episodes, and this is the formula. This is the formula for temporal difference. Okay, I think R is the reward in the next step. I'll just check, wait. In the next example, I'll get to you. So what is the difference? Of course, Monte Carlo, you have to wait for the episode or the game to end. In temporal difference, you don't have to wait for the episode or the game to end. You make an estimate straight away using the immediate reward plus estimated value of the next state. Okay, so total future reward is not known. So again, as I said, I was discussing chess. I mean, Monte Carlo is like waiting until the chess game ends and it sees whether you lost or you won. And then it will adjust all your moves based on that final result. But temporal difference, it will analyze like this. See, okay, I have moved my say bishop or say knight over here, and it looks like that I gained a better position on the board right now. So I'll probably adjust based on this expected score. Okay, so that is the whole idea behind temporal difference. Now, what is alpha over here? What is alpha? Alpha is called as the learning rate. So basically, it adjusts how much you can say the old estimate should be adjusted based on new information that is controlled by alpha. What percentage of adjustment is done, or what percentage of learning is done, something like that. Okay, so you can see that in both the cases, whether it is Monte Carlo or temporal, in both the cases, the structure is not very different. New Q value is equal to old Q value plus alpha multiplied by something minus old Q value. Now, the only thing is that now if I write over here, new Q is equal to old Q plus alpha multiplied by target minus old Q. Now, the only difference is that in this case, the target is R, and in this case, the target is R plus Vs dash. We'll see this in example. It will make it very clear. Okay, so if alpha is small, it means that we learn very slowly. We make very small adjustments each time, but the estimates are stable. But if alpha is large, like say 0.95, we adjust almost fully based on the most recent experience. We learn very fast, but our estimates might be very unstable. They might bounce around. Okay, so that's the difference. Okay, so how much weight you want to give to the new experience, that is your alpha. So your trust level in new information versus old experience. That's it. Now, the example that I was talking about. How do these updates in Q values work using these two methods? So, as an example, let's say we have four states and three actions, and that the current values are indicated in the table given alongside. So, these Q values 0.1, 0.2, what are they telling you? They are kind of telling you how good it is to take a particular action in a particular state. Of course, a higher Q value will kind of, not always, but kind of generally always, no, not always, sorry, kind of generally involve higher expected rewards in the long run. Okay, if they are updated to a lower number, that's a different thing. But almost in all the cases, it will imply higher expected rewards in the long run. Okay, so let's start with Monte Carlo. Suppose Suppose on the next trial, action 3 is taken in state 4 and the total subsequent reward is 1. Total reward is 1, alpha is given as 5%. So, next trial, action 3 is taken in state 4. If you are in state 4, you take action 3, it means this Q value is being referred to, and you care about the total subsequent reward after this. You don't care what reward I will get immediately after this state. No. Subsequent reward is not important. Total reward is important. Okay. So it's given to be 1. Total reward is given to be 1. Okay. So the table says that the current estimate is 0.8. Okay. For Q4 comma 3. Now, after taking this action, you've observed that the total future reward is going to be 1. And as I told you in Monte Carlo, you will have to wait until that final result, that final reward is realized, and then you will adjust your estimate. So make sure that this thing is, because see, the final reward cannot be known in advance. It has to be known after the episode or the game ends. So the adjustment that you will do, that you will do after the episode. Okay, so what is the adjustment? This is the formula and this is the adjustment. 0.81. So you can think of this like you thought that okay, uh, if you took action 3 in state 4, you probably would have gotten a total subsequent reward of 0.95. That is what you thought. Okay, but then you got a total reward of 1. Okay, no, in fact, I think I should refine my explanation a little. I think you believe that okay, you only know that this is the reward, okay, for this particular action. So you are only concerned that okay, I took this decision, this action in this particular state, and I just thought that I will eventually get 0.8, but finally I got to 1. So obviously after this step I got even better. So uh, let me just increase my estimate a little bit for this particular action, because this is a better action. Now I've realized it. So it means that I'll try to update my belief that okay, this is a good action. So I mean, you can think of it like anything. I mean, probably you had a model where you thought that okay, this model, uh, or for that matter, I should not say model. Let me just give a more practical example of mm, daily scenarios. Say we after this lecture is over, we'll go for lunch, and let's say we want to have lunch outside after this long session. Okay, so there is a store, there is a restaurant nearby where I want to go, and there is a lot of traffic jam. And I decide, okay, there are three, four alternative routes, and I thought I have a previous estimate that okay, there are four routes, so route three is the one which I want to take right now, and route three probably would help me to reach that restaurant in 15 minutes, let's say. Okay, but then I when I go to route through route three, and I see that okay, the total time that I took was 13 minutes. So it is actually a better outcome. So I'll slightly update my belief that this route is better. And mind you, again, when I talk about 13 minutes, that's the total subsequent reward. And this might you might get a little confused into believing that see, when I thought that it will actually lead 15 minutes, then I'm only talking about the current action and current step. So that also, when I said that 15 minutes I'll take, that also I'm referring to the total time, right? So why not? I'm distinguishing between the total time and the time from any particular street. So again, the refinement over here is that when I take route 3, maybe in route 3, the confidence that I have of 15 minutes is only because of say two streets which help me in reducing my time a bit, and those two streets only are say one is 5 minutes, one is 7 minutes. So those two streets themselves, I thought that they will take almost 12 minutes to go through. So the action in the next state can be 5 for me, 5 or 5 plus 7, 12. Try and understand the reward, sorry. In terms of points, I think it will be the inverse, because in terms of time, it is, if it is becoming less, then in terms of points it will become more. So the idea that I'm trying to say is, let's say my chosen route has four streets to in total. In those four streets, I chose that particular route 3 because I thought that the the portion of the road which is jammed, that portion of route 3 will take only 12 minutes in total, 5 plus 7, whereas for the other routes it will take even more. But because I was able to reach in 13 minutes total, it means that probably in those two streets I took less time as well. So that is why I will update my belief of entering into that street and finally choosing that particular road. I will update the points to a little bit on the higher side. So this is a very layman practical kind of example. Okay. So you are using your experience that, okay, this is a good road. This will help me in the traffic jam. But then when the outcome is even better than you expected, you are updating your belief similar to what we had in Bayes theorem when we were updating probabilities. It's quite analogous. I'll not say similar, a little bit analogous as far as beliefs are concerned. Now, let's say we want to go for the temporal difference update. So again, we start at the same state action 3. So this is the one which we are referring to initially. But instead of waiting until the end, we look immediately after this step. So we land in state 3. We are in state 3, and in state 3, the immediate reward that you get is 0.2. Okay, so earlier you were in state 4. You know that after taking the next step, you will be in state 3, and the immediate reward, the subsequent reward, will be 0.2 between these two decisions. Now, this part I said is very important, which Garb should have emphasized, because how they chose this number of 0.9, it is mentioned that we would note that the value of being in state 3 is currently estimated to be 0.9. This is a bit confusing. If you write it like this, it is not correct, because the value of being in state 3 can be any of the three. That's why In the PDF, I've given a different example. I've changed the numbers a little bit. Numbers I've changed. I've also given which action I am taking. Okay. But in this case, how they have chosen it to be 0.9 is because of this idea. So if you don't know which action you have to take, you have to make sure that you take that action which maximizes this expression. So you have to choose the max QSA value. So out of these three, in state three, this is your max QSA value, and that is why 0.9 has been chosen. This is your max Q3 star. Star is any action which you can take. Okay, in this case 3 comma 3. So that is the idea. Okay, now what will be the update? What will be the update? How promising your uh, state 3 is now? So obviously the best estimated value is 0.9 as we have seen. So based on this 0.9 now, you will update the Q4 comma 3, this value you will update to 0.815. So R is the subsequent reward. Zero point 0.9 is the value, max value in the next state. Okay. And this is the idea over here. So in case of Monte Carlo, we were waiting till the end for the final outcome. Temporal differencing is analogous to bootstrapping. You are saying that, okay, I got a small bonus of 0.2 right now. And the place that I landed looks promising as well, 0.9. So overall, this move was a bit better than I thought. I'll slightly raise my estimate of 0.8. Okay, so basically, when you are going to a different to the restaurant, let's say if you turn and in the middle only you have to take another decision. Let's say you find a road which is jammed, and then you suddenly turn on a new street, and immediately you see that okay, as soon as you turn, you see green lights ahead. There will be a psychology that you start to feel optimistic about your route being faster. It may be a coincidence, it may be real, you don't know. Time will tell that if signals are actually, they what kind of idle time they have and what is their switching time. That time will tell. But as of now, you start to feel more optimistic. Okay, so these two things, whether it is Monte Carlo, it is, of course, it waits till the end, so it's very good for tasks like games, episodic tasks, whereas temporal difference updates immediately. So it is great for tasks where you cannot afford to wait. Okay, and these example, this particular example for that matter shows that how learning can happen step by step. Either you can wait for the final outcome or you can peek ahead one move at a time. But learning is still happening step by step. So is the idea clear now? Is the concept clear to some extent? Okay, fine. Okay, this is complete theory. You can just go through it yourself. Finally, we'll conclude by discussing the differences between unsupervised, supervised, and reinforcement learnings. So unsupervised helps you to identify relevant features. Supervised, prediction or classification. Reinforcement, making decisions based on trial and error. Okay, exploration and exploitation. It is used broadly for classifying the data into two groups. It is mainly used for prediction and to some extent for classification also. It is used as a decision making tool. These are the examples: K-means clustering, principal component analysis. And for over here, we have lasso, logistic, and over here we have value-based learning, decision-based learning, etc. Okay, thank you for this session, attending the session. Any questions in QTA 14 only? Only QTA 14, any question in this lecture?
So generally, what is the weightage of this QTA 14 topic on the final exam, historically, in general?
You can expect 3 questions from the last 2 chapters at least. As I always say that we should not rely on selective study and weightage can be bit variable. In fact, I was having a part 2 customized study plan meeting day before yesterday. 3 candidates, all from MidhaFin only, they passed part 1. Uh, So three candidates were present in that meeting. Okay. So those three told that uh, in part one, there were chapters. I mean, just like I've written on Kura also, and I've told this multiple times. And this time it happened particularly even more. Theory questions were very high. 80%, more than 80% theory questions were there. But there were many chapters where questions were not at all asked. And there were chapters where multiple questions were asked. For example, this time he told that, I think it was, if I'm not wrong, it was Shivam. Yeah. In Shivam's set, binomial trees, only a single chapter was having, I think, three questions or something like that. He was. So you can never predict. But if you take an average, I'll say, as you ask for an average number, I'll say three questions from the last two chapters. Okay, Ajit.
Got it. Thank you.
Yeah. Anything else? Okay, thank you. So we'll just end this session. Thank you.